Okay, so Schrödinger used his equation to predict the shapes of orbitals, is what we call them, where the electron is likely to exist, and he predicted all these things out. And this big chart here is going to show us all the different orbits that his mathematics predicted. So we can see at the smallest level there's just spheres, and every time we go up another level, the spheres get bigger and bigger and bigger. At the second level, we have spheres and dumbbells. At the third level, we have spheres, dumbbells, and these D shapes. At the fourth level, we have spheres, dumbbells, these D shapes, and these F shapes. And these are all just mathematical results of treating the electron like there's a wave that defines its position, and then keeping the total energy of that wave constant, kinetic energy plus potential energy, turning into total energy. With all of these new ideas and all of these new structures that show us where the electrons exist around atoms, we needed to come up with some sort of way of representing these shapes simply. And so the first way they did that is with what they called the quantum numbers. There are 4 quantum numbers, and using the 4 quantum numbers, we can specify the location of each of these individual, or we can specify any one of these individual orbits. So the first quantum number is called the principal quantum number, and it gets the letter n. N is tied to 2 basic things: the size of the orbit, where 1 is small, and it goes all the way up to 7, which is large. And n increases, or n basically is set to the integers 1, 2, 3, all the way up to 7. It also represents fundamentally the energy of the orbit, where small orbits have low energy and large orbits have high energy. That's the principal quantum number. The secondary quantum number, L, represents the shape of the orbit. This is also related to the angular momentum of the orbit, but we're not really ready to talk about that, so we're just going to leave it like that. L has 4 values. It can be 0, 1, 2, or 3, where the 4 values correspond to the 4 different types of shapes. So here, for the sphere shape, we use the L equals 0. For the dumbbell shape, or the P's, we use L equals 1. For the D's, we use L equals 2. And for the F's, we use L equals 3. Now, what we can see is not all n's have all of the L's. So there's some restriction here on L, where L can range from 0 up to 1 minus the value of n. So for example, if n was 3, then L would be able to be 0, 1, or 2, but it would stop there because that's 1 less than the value of n. If n was 5, then L would be able to be 0, 1, 2, 3, and even mathematically 4, even though there aren't any elements that go up to that level, and so we don't include it. The magnetic quantum number, or ML, lets us know the orientation of the orbit. For an S, there's only one orientation, because no matter which way you rotate a sphere, it's the exact same. For the P, we have 3 orientations. For the D, we have 5. And for the F, we have 7. You can see the pattern here, 1, 3, 5, 7. And we can relate these to the L's. So this is L equals 0, L equals 1, L equals 2, L equals 3. And so trying to figure out how we can translate those into the right number of orientations, we come up with the restriction for ml, where it goes from negative L through 0 up to positive L. So for example, if we're dealing with an orbital whose secondary quantum number is L equals 2, that orbital would have 5 possible orientations. We can see these 5 orientations as they correspond to the d orbitals: 1, 1, 2, 3, 4, and 5. If L was only 1, then ML would range from -1 to 0 to 1, representing the 3 possible orientations, -1, 0, and 1, of our, that's not actually correct because they have whatever, the 1, 2, 3 orientations associated with our 3 p orbitals. Finally, because they figured out each one of these orbitals can hold 2 electrons, they made up one more orientation number, which would be the spin number. In spin, well, quite frankly, it's complicated, so we're not really going to discuss it. But what we're going to say is that this one can be +1/2 or -1/2. And that way, every electron around an atom will have a unique set of quantum numbers. So let's look at these quantum numbers. Let's make up some values, and then we can see how the quantum numbers correspond to our notation SPDF and which one of these that actually corresponds to. So let's just say, for the sake of an example, that n equals 4, L equals 1, ML equals -1, and MS equals +1/2. So n equals 4 tells me that I'm in this row. L tells me that I'm dealing with one of these 3. -1 tells me which one, so let's make it this one. And the +1/2 tells me that it's one of the 2 electrons that could possibly be in this orbital. So that's how we use quantum numbers to specify locations. Translating this to our SPDF notation, we would call this a 4p, and this -1, we could put x, y, or z down here, so we'll just put x, and then the 1/2 just tells us we only have 1 electron that we're considering right now. If there was both the plus and the minus, we would put this up to a 2. One more time, let's say we're dealing with an n equals 3 electron. Its L value is 2, which just needs to be anything that's 1 lower than the n value. Let's make its ML +1 and its MS -1/2. So again, n equals 3, L equals 2 tells me I'm dealing with one of these d orbitals. In which one of them depends on this 1, and right now that's telling us it's either this one or this one, and the -1/2 isn't telling us much of anything. So let's just pick this one for the sake of argument, and that's where that electron, or that's the shape that would dictate the position of that electron around the atom. It would exist in one of those 4 shaped, I don't know, what would you call those, ovoids. So that's the system of quantum numbers they made up. That's how it relates to the orbitals that were predicted by the Schrodinger equation. And so that's how we can specify the location of an electron, or at least the location where that electron is likely to be, or the probability wave that represents the position of that electron.